Alright, so in this video for 4502, we're going to actually solve for the eigenvalues and eigenvectors of the harmonic oscillator. In class, we've talked about the solutions to this particular problem and how we can use them to model how molecules vibrate, but we didn't derive the solutions. And the reason is that deriving the solutions may be satisfying, but it's ultimately not a skill that we're going to be tested on. So this entire video is completely optional, only really watch it if you're genuinely interested in the material. So what we're going to be solving is looking for the special eigenfunctions, the harmonic oscillator, H, that's dead, we're looking for the psi sub n, where our Hamiltonian is a harmonic oscillator Hamiltonian, and just as a reminder, HO is equal to minus h bar squared over 2n times the second derivative operator plus 1/2 m omega squared x squared. Okay. And so we're looking for the particular type of function where when we multiply it by this operator, act on it with this operator, we get a number times the function back itself. And the method that we're going to use to solve this is something called the Frobenius method. It's a method for solving second-order differential equations. And the idea here is that we are going to, step 1, determine the behavior of the wave function at its asymptotes. So what does that have to look like? How does that have to behave as it goes to plus or minus infinity? And we're going to determine its asymptotic behavior is going to be some function of x. And then we're going to write psi, some other function of x, times its asymptotic behavior. And then the third thing we're going to do is we're going to expand g of x as a power series. Okay. And so we're going to write it in terms of a set of coefficients times polynomials. And when we do this, we're going to keep one thing in mind this entire time. We'll come back to it twice during this derivation. And that is remembering that psi star psi, the integral over all space, we're going to need to be able to normalize it. So if we end up with some function that's unnormalizable, we're going to have to change our plan or redo our approach or just check in. Okay? Alright, so that's going to be our goal. So let's move over here. I think we can keep this in view while I write on the right hand side so we can go back and forth between them. Okay, so let's go back to our harmonic oscillator Hamiltonian. So h hat minus h bar squared over 2m d by dx squared plus 1/2 m omega squared x squared. So that's our Hamiltonian. What we want to do is we want to make a change of variables to make this dimensionless. We want to find a dimensionless variable that gets all of these constants out of the way. And so what we're going to do is we're going to introduce a variable c. And c we're going to call it equal to the square root of m omega over h bar times x. Okay. Now we can also, in order to evaluate this, we're going to need to know what d c is, and d c is equal to the square root of m omega over h bar dx. Okay. So we can use this change of variable to rewrite our harmonic oscillator Hamiltonian, and let's go ahead and do that. So it's second derivative of psi with respect to c squared ends up being equal to c squared minus 2e over h bar omega times psi. Okay. Alright, so we have the second derivative is equal to a function of c squared minus some constant times the wave function. Now we're going to make one other substitution here, and we're going to say let the number k be equal to 2u over h bar omega. And so then we can rewrite this as c squared minus k times psi. Okay, so this looks like a more straightforward differential equation. And what we're going to do is we're going to go back here to step 1, and we're going to determine the asymptotic limits of this. So what does this look like? What must this look like as c gets really large? Okay, so what is that limit as it goes to infinity? Well, in the limit that c gets really large, this portion that looks like k doesn't matter at all, right? If this goes to infinity, infinity minus some number is still infinity. And so we can approximate d squared epsilon squared psi. And the limit of c gets very big. And this has a easy solution that we can write down. The solution to this differential equation would be psi c is equal to a e to the minus c squared over 2 plus b e to the plus c squared over 2. Okay. And you can verify for yourself that if you take the second derivative of this, you get c squared times psi. Okay, so it turns out that only one of those is a useful solution to us at this point. If we were to plot what those look like in the asymptotic limits, when c gets really big, move this up a little bit, we can plot these two functions. Let's plot a e to the minus c squared over 2 is a Gaussian, and b e to the plus c over 2 squared looks like that and goes up very steeply. This function is normalizable, and this function is not. The area under this curve clearly goes to infinity. And so we're going to throw this solution out as being unphysical. And I'm totally okay doing that. And so we can say in the limit of large c, or limit of large x, our wave function has to look like this. It actually has to look like a Gaussian in the limit of long extension or compression. Okay. Alright, so now that we have that, we're going to rewrite everything. We're going to rewrite our wave function as some other function times its asymptotic behavior. So we're going on step 2 now. Psi goes to, call it g of c times a e to the minus c squared over 2. Okay? So we have our function that's how it behaves non-asymptotically times its asymptotic behavior. And now we're just going to actively put this into our Hamiltonian. So we're going to write what happens when we do the following. We operate on g of c a e to the minus c squared over 2. What does that look like? Alright, so the first thing we need to do is we need to figure out what the first derivative of c is. So, sorry, the first derivative of the wave function, d psi by dc. If this is psi, then we need to use the product rule for taking this derivative. So that's going to be equal to dh by dc minus sorry, we call this G, sorry, dg c minus c g of c times whole quantity times that Gaussian. Okay, and we can take the second derivative of that as well. So we look at the second derivative, d psi dc squared. Again, we need to use the chain rule here, so we get the second derivative of g of c. We need to take use the chain rule, or the product rule here, and so we're going to get minus 2 c dg of c dc plus c squared minus 1 times g of c, and then all of that times our Gaussian. We take that second derivative. So now that we know what our second derivative is, we can plug that back into our Schrodinger equation. And hold on a second, while we're back on here. You'll notice that when we take the second derivative aside, this Gaussian component stays out here. And so if we look at, if we go back to our original Schrodinger equation here, right? We can take the second derivative with respect to c, and then take this to the other side, and when we subtract this, this has to be equal to 0. But that Gaussian component is never going to be equal to 0. And so we can, when we put this back into our Schrodinger equation, we can write down that the second derivative, keep doing that, second derivative with respect to c minus 2 c times dg by dc plus k minus 1 times g is equal to 0. We can pretty much, we can ignore the Gaussian at this point, and we get down to this differential equation, which only involves our non-asymptotic portion, our g. Oops, sorry, that went off the slide a little bit. Okay. And now what we're going to do is we're going to, this is still completely equivalent to the Schrodinger equation. We're now going to write g as a power series. So g is equal to a0 plus a1 c plus a2 c squared dot dot dot. The sum over n equals 0 to infinity a sub n c to the n. So we're just going to do a power series. So I can take the derivative, right, we're going to need the first and second derivative of this, so let's go ahead and do that. The first derivative of g is going to be equal to a1, right, that goes to 0, that comes a1 plus a2c dot dot dot, sum over n to infinity times, oh, sorry, that should be 2a2 n times a sub n times c to the n minus 1. Similarly, we can take the second derivative and that's going to be equal to sum over n equals 0 to infinity n times n minus 1 in n minus 1 a sub n to c to the n minus 2. Okay, I'm going to take that second derivative. Sorry about that. Okay. So, now we're going to use a little bit of a trick here. Okay. The trick is that this series, right, when we start at n equals to 0, this is 0. And n equals 1, this is still 0. When we go up here, right, we started this at n equals 0, but that first term is just 0. Okay? And we can rewrite this series by replacing n, j, or we're going to replace j equals n plus 1. Okay? And then we can rewrite this as the second derivative is equal to the sum j equals 0 to infinity, j plus 2, j plus 1 times a sub j plus 2 to c to the j. And so you can show that these two are entirely equivalent. We're just doing what's called a level shift. We're just changing where this power series starts at, since some of the first few terms were 0. Okay. Putting this all together, right, we can put all of this together for our differential equation, and what we can end up saying is that the sum over j equals 0 to infinity, j plus 1, j plus 2 times a to the j plus 2 minus 2 j a sub j plus k minus 1 a sub j, all of this times c to the j is equal to 0. Okay? Alright. The only way that this can be true is if these coefficients add up to be 0 for every value of c, right? Because it has to be true over any value of c. So these coefficients must always add up to be 0. And so we can rewrite this as j plus 1, j plus 2, a sub j plus 2 minus 2j a sub j plus k minus 1 a sub j has to be equal to 0. And we can therefore write a sub j plus 2 as a function of a of j. It's going to be equal to 2j plus 1 minus k divided by j plus 1, j plus 2. All of that times a sub j. Or in other words, this is a recursion relation. So if I know a sub j, I can find a sub j plus 2. Okay. So it's a second order differential equation. So we get two arbitrary coefficients, right? So we have to pick a number for a0 and a number for a1, and we can do that. If we start with a0, then we generate all of the even coefficients. If we start with a1, we generate all of the odd coefficients. However, we still have to ask the question of, is this normalizable? So now we have this function these are different coefficients for the different terms in the polynomial, and we're adding them up, j equals 0 to infinity. If we take the limit that j goes large. We can write a sub j plus 2 is approximately 2 over j a sub j. Right? So in the limit of large j, we have all of these different polynomial terms, no problem. But it turns out that this is the same limit as the original solution that we threw out. So if we were to take b to the e plus c squared over 2 and expand that as a power series, and look at large n, we would get the exact same limit. Okay? So the only way that this solution can be satisfactory is if for some value of j, all of the other a sub j's are 0. Okay? So if there are certain, the only thing here that's unknown right now is k, which is the energy. It's 2 times the energy over h bar omega. If the energy is fixed, so that for some value of j, this term becomes 0, then every other term in the series after it also becomes 0. Okay? So if we let k equal 2n plus 1, where n is just an integer, then we can plug this in and we get e is equal to n plus 1/2 h bar omega. And we can plug this back in, we can plug this back in to our polynomial recursion coefficients. Okay. And that a sub j plus 2, 2j plus 1 minus 2n minus 1 over j plus 1 times j plus 2, right? Times a sub j. If we look at this, when n is equal to j, this goes to 0. So when n is equal to j, a sub n plus 2 is equal to 0. Right? So this kills the power series. Okay, now this seems like a really odd way to find the solutions. Right? But really what's coming out of here is that we're getting a quantized energy. The energy becomes quantized in order to enforce the normalization condition, which in this case is that the psi of plus or minus infinity needs to go to 0, which is our boundary condition. So once again, we have the boundary conditions here giving us quantization of the total energy. Okay, so let's look at how we can actually get some of these polynomials out, and let's see if they match the same solutions that we showed in class. Okay, so let's start n equal 0. If n equals 0, then a2 is equal to 2 times 0 plus 1 minus 2 times 0 minus 1 over 0 plus 1, 0 plus 2 times a naught, which is equal to 0. So a2 is equal to 0, and psi naught is equal to a naught e to the minus c squared over 2. Okay. Let's look at psi. If we go n equals 1, we're going to be on the odd side of our recursion function. So we're going to start with A3. Now we're going to look at the j equals 1. So we're going to get 2 times 1, so that's 2, plus 1, that's 3, minus 2 minus 1 over 1 plus 1, 1 plus 2, A1. So let's plug this together. We have 3 minus 3, 0, and so psi 1 would be equal to A1 c e to the minus c squared over 2. Okay. Let's look at n equals 2. We're back on the even side, so we're going to go back and looking for what A2 is. A2. Alright, again, so at this point this is a of j plus 2, so our j is going to be equal to 0. So 2 times 0 plus 1 minus 2n, that's going to be 4 minus 1 over 0 plus 1, 0 plus 2, a0, to minus 2, a0. And so our wave function, psi 2, is going to be equal to minus, here, a0 times 1 minus 2 c squared times e to the minus c squared over 2. Okay? Alright. And then our psi, for psi 3, if we want to let n equal 3, let's do n equals 4. That's going to be better. N equals 4. And let's look for what that's going to be. So we're still going to be on the even side of things. A2, 2.0 plus 1 minus 2 times 4 is 8 over 2a0 minus 4a0, and a4 is going to be equal to 2 times 2 plus 1 minus 2 times n, so again minus 8 minus 1 times a2 over, here, 2 plus 1 times 2 plus 2, so that's 3 times 4, that's 12. So we have 4 plus 5, 4 minus 8, that's minus 4. Let me see, make sure I get this right. Minus 4 over 12, right, j, which is equal to minus 1/3 a2, which is equal to 4/3 a0. Right? Okay. And so then we can rewrite this as psi of 4 is going to be equal to a0 times 1 minus 4c squared plus 4/3 c to the 4th e to the minus c squared over 2. And so this is how we can use this to find the wave functions. At the very end, you can resubstitute. Remember that c is equal to the square root of m omega over h bar x. And the last thing we would need to do for each one of these is normalize them, but that becomes tedious very rapidly. And so by solving this method, we've come up with the same Hermite polynomials that I gave to you in class, but you can see that the method is at best somewhat tedious, and since it's not relevant to solving other differential equations in the class, we decided not to really pursue using class time on this. If you have any questions, feel free to contact me by email or see me in office hours. I'm happy to talk about this method of differential equation solution. I just want to keep it out of the classroom. Hope this helps, and I'll see you in class. Bye.